Hello and welcome to EcademicTube. In this question it says that in this example we consider the design of the current source that supplies the bias current of a MOS differential amplifier. Let it be required to achieve a CMRR of 100 dB, that is it is in decibel, and assume that the only source of mismatch between Q1 and Q2 is a 2% mismatch in their W by L ratios. So let I is equals to 200 microampere, that is the bias current, and assume that all the transistors are to be operated at the overdrive voltage, that is the VOB, equals to 0.2 volt. Now for the 0.18 micrometer CMOS fabrication process available, now this is the fabrication process which the transistors are being fabricated in. What kind of technology it is the 180.18 micrometer, or we can say it is the 180 nanometer, and the early voltage VA dash is given as 5 volt per micrometer. If a simple current source is utilized for the current I, so what channel length is required? If a cascade current source is utilized, what channel length is needed for the two transistors in the cascade? So we shall quickly be going to the solution of the question. So first of all, let us draw the differential. We can see that in this question it is written given as MOS differential amplifier. So we shall be quickly drawing the circuit first of all. So the question is, this is the VDD, this is the resistance, and we have this the MOS differential amplifier. This is this source resistance RSS, and the common mode input voltage, this is the VICM, which is the common mode input voltage, VICM. So this VICM is the common mode input voltage. So we have this RD, this the drain resistance, and we have the output over here, that is the taken over the drain terminals. So this is the output V0. So this is the entire circuit. We can see that now what we'll be doing is we shall be drawing the small signal equivalent. Now as you can see that the source terminal, which is this is the source terminal, this is not grounded. So as the source terminal is not grounded, so we shall be drawing the T model of the MOSFET. So the T model, as we know that if I am drawing, I am drawing just a quick diagram of it. So this is the IS current, this is the source current, and this is the 1 by GM resistance, and this goes to this source terminal, this is the drain terminal, and this is the gate terminal, and we know that the gate current IG is 0. So this is the T model. So we shall be drawing for the two circuits of the differential amplifier. So the circuit will look like, the drain resistances are connected to ground, this is the RD, and this is the current, which is IS, or you can say that we can take it to be I, and this is the resistance, which is nothing but 1 by GM, and this one is the gate terminal. This is grounded because we know that for small signal equivalent all the independent voltage sources are shorted and independent current sources are open circuited. So it is, as we know that this is the voltage source, so these two will be shorted to ground. So this is the 1 by GM, and this is the RSS. So we have current I going from here, because this towards the gate terminal, zero current is going towards the gate terminal, because due to the oxide capacitance, this is due to the oxide layer. So as oxide is an insulator, so zero current flows through the gate terminal. So this entire current will be flowing from drain to source, and for the other half we shall be drawing the same thing. so it's also grounded, and it is 1 by GM. So both current I and current I over here comes, and at this terminal this I plus I, that is 2I current, flows over here. So this is the basic circuit. Now if we take the half part, that is if we take only the half circuit, so if we consider this circuit only, so if we consider this part only, so we shall be having the next circuit, which is the half part. So I am drawing over here, this is the resistance, and if we draw the circuit diagram, so this will look like, this is the RD, this is the VICM, and this is ground. So this is the half part, and I am drawing the other half part. This is the VICM, this is the resistance. Now you can see that this RSS resistance has been divided into two parts, this resistance and this resistance. So now we need to find the value of these two resistances. So if we take now these two resistances, we can mark it as R, and it is an R. Now if we take R is equals to 2 RSS, so the combination of the, now we can see that this R and this are in parallel combination, because this actually goes from here. We can see, we can write it like this as R and R. So this combination of R into R, which will give R by 2, this should be equals to RSS, because from RSS single resistance we are getting two resistances which are in parallel. So this R by 2 should be equals to RSS, so R should be equals to 2 RSS. So we finally got the value of R. So this is our 2 RSS, and this is also 2 RSS. So this is our half part circuit. So for computing the common mode gain, we consider the half part circuit. Now coming back to the question, we can see that it is given a mismatch. So let's go to the question again. So there is a mismatch given in their 2% mismatch given in their W by L ratio. Now we need to go from to our basic fundamentals. So we know that a mismatch in W by L results in a GM mismatch. Now why did I say it like that? Because the transconductance GM is given by the formula 2 mu n COX W upon L into the drain current. So we can see that there is this parameter mu n COX, then W by L ratio, and the drain current. So if there is a mismatch in the W by L ratio, so there will automatically this GM will change. Now what is the meaning of this mismatch? Mismatch means this W by L ratio gets changed, that is the new W by L ratio is the old plus some delta W by L. So this will, due to this there will be some change in the W by L ratio, and due to this change we will be getting a new GM. So that's why it is known as a GM mismatch. So we shall be calculating, so there is W by L mismatch is given, so from there we shall be calculating the GM mismatch. So it is seen that an error of 2% in W by L will result in an error in GM of 1%. That is, the 2% mismatch in the W by L ratios of Q1 and Q2 will result in a 1% mismatch in their GM values. So in the resulting CMRR can be found from equation 9.88. So we can see that this, so what we can see that this W by L ratio's mismatch, we have 2%. So if we multiply this 2 into 2%, we'll be getting overall of 4, uh, that is our 4%, and there will be this the mu and cox parameter and id. So overall we will be getting a mismatch of 1% for the gm mismatch. So now we shall be calculating. So we have the formula for CMRR. Now CMRR is the common mode rejection ratio, and as you all know that it is the ratio of differential gain by the common mode gain. Now this formula we shall directly write it as like this: 2 gm RSS divided by delta gm by gm. Now this formula is given in the Cedra and Smith book of microelectronics, so it can be referred from that part. It is in the chapter 9 itself. So due to this gm mismatch, that is gm1, that is the, we can see this part, if we write it as q1 and it is q2, so it will have gm1 and gm2. So gm mismatch means this gm1 will be the earlier old gm plus delta gm, and gm2 will be old value minus delta gm. So now we can see that the gm values of two transistors are not same, because one is a bit higher than the old value and the other is a bit lower than the old value. So from this CMRR we shall be calculating. Now CMRR is given as 100 dB CMRR. So we shall be taking the magnitude value, which is nothing but 10 to the power 5, and it is nothing but 2 gm RSS divided by, so delta gm by gm is nothing but 0.01, because 1% mismatch in gm, because 2% mismatch in the W by L ratio, so there will be 1% mismatch in gm. So 1% mismatch is correspond to the value 0.01. so now how to find the value of gm? So we know that gm by the formula 2 id drain current divided by the overdrive voltage. Now this id, we shall be going to the circuit again. So this is the id. So this 2i value is given, this 2i value is given as capital I. So obviously this will be I by 2 and this will be I by 2, so their sum will be equal to a capital I. So we shall go into the formula 2 into I by 2 divided by the overdrive voltage. So our I is given 0.1 milliampere and overdrive voltage 0.2 volt. So we will be getting gm of 1 milliampere per volt. So this will be substituting, this value we will be substituting in this equation, and now we will be getting 10 to the power 5 is equals to 2 into 10 to the power minus 3 into RSS divided by 0.01. So we will be getting an RSS value of 500 kilo ohm. So this one is the value. Now we shall be going. Now if the current source is implemented with a single transistor, so it will have a drain to source resistance, which is the R0. R0 is the drain to source resistance. We know that R0 is nothing but the early voltage divided by the drain current. So this R0 will be equals to RSS, and this is equals to 500 kilo ohm. So now we shall be replacing the formula of R0. So VA by I, which is the drain current, is given by 500 kilo ohm. Now you might think that I have written here only the I. Now why I haven't written I by 2? Because this RSS, this entire RSS is replaced by R0. So here it will be VA divided by ID, that is the current flowing through this RSS, which is nothing but the capital I. That's why I have replaced ID with capital I and not I by 2. So VA will be getting from this equation, VA will be 100 volt, because I is given to be 200 microampere. So now, so our early voltage will be 5 into L, because our early voltage VA dash is given as 5 volt per micrometer. So accordingly we shall be multiplying the length, this voltage, with the length of the transistor, that is 5 into L. So here, from here we shall be getting L is equals to 20 micrometer. So we got the value of L now, which is very large. 20 micrometer is a very large value, because we are dealing this MOSFET transistors in our IC chip in the dimensions of nanometer, and it is in micrometer, which is very large. Now we shall be so our assumption is wrong, because we took this RSS to be R0. Now what we'll be doing is we will be taking this RSS to be a cascade current source. So we will be replacing this RSS with a cascade current source, that is if we go to this circuit here, so this resistance will be replaced by like this will be replaced by like this. This entire resistance will be replaced by a cascade current source. So we know that for a cascade current source, its resistance, output resistance, is given by GM R0 into the R0, which is nothing but the GM R0 square. Now here again we need to calculate the GM, because this GM and the earlier GM we calculated are not same, because the currents are not same. So this GM will be is equals to 2I divided by the overdrive voltage. So after calculating we will be getting 2 milliampere per volt. So from here, if we equate it, 500 into 10 to the power 3, it is nothing but 2 into 10 to the power minus 3 into R0 square. So now we shall be getting R0 is equals to 15.8 kilo ohm approximately. Now we shall be calculating again this early voltage VA by I, which is nothing but 15.8 to 10 cube. So now we shall be getting this early voltage to be 3.16 volt. So again we shall be calculating the length, which is nothing but our 3.16 divided by the VA dash. So we shall be getting 0.63 micrometer. So we can see that here, just by replacing R0 with a cascade current source, we are downgrading the length, or we are reducing the length from 20 micrometer to directly 0.63 micrometer. So this is a huge reduction. So by simply replacing a resistance with a cascade current source, we are bringing down the dimension of length from a two-digit micrometer to a decimal point micrometer. So our final answer will be L is equals to 0.63 micrometer, and this is a practical value. Thank you.